Okay, I expected not so many people to participate in my workshop. Basically, I thought about making it something like class style and just having people asking questions and also have some very strong feedback loop. But I try to do it anyway, and if it does not work out, I will just maybe stop earlier, and people who want to explore some more perf features can just come up to me and we can sit somewhere and try out stuff. But for those people who are now trying to participate, what we need so far is that either you have a recent Linux kernel installed on your system which has all the config perf features enabled and also is compiled with debug info support. A lot of distributions actually ship with out of kernel debug information. So for example, if you have Fedora, you can just debug info install kernel, and it will download all the packages necessary that you have full debug info information on your system. We will need some more packages, so we will at some point see ph hole, which is provided by the drafts package in Fedora at least. I guess it's also easy to find that in Debian or in other packages. Who of you already knows about PA hole? Who uses that? Okay, not so many. Okay, so I guess the biggest problem nowadays for perf is that, at least if I talk to people or try to show people what perf can actually do, is that the debug information is correct. And nowadays it is like that the compiler always embeds a specific build ID into the system, into the object files. And the object files then can kind of get hashed in this specific path. Can you see the mouse pointer? So in this specific path, user lib debug build ID, and oh, you cannot. I just switched to mirror mode. Sorry. Okay, my television went out. So basically, we have a direct user lib debug. I guess it's the same for a lot of distributions today. And in there, we have a build ID directory, which basically is kind of a hash for all the debug information we have on such a system. And so perf uses that quite a bit to display or let you find specific variables which are used in the source code, so you can actually trace specific variables later on in the system. That's basically pretty easy to manage. So in Fedora, for example, if you see debug info packages, they basically just install all those hash files. And later on, all the kernel modules are basically also installed, which debug with debug information. And the perf utility, or mostly all elf utilities, just do a side lookup into the debug cache and then resolve the debug information. So I don't know. There was work also to make this a bit less verbose, because debug information are quite heavyweight on the system and consume quite a lot of storage. And so, for example, Solaris has smaller, they have a specific debug system, debug information like way, which is embedded into the kernel, which they use in dtrace. And I don't know what Linux will do there in future, but currently debug info is the way to go. There are also some commands which you can use to actually deal with this. So basically, build ID list and build ID cache. It allows you, if you have, for example, specific programs where you are not able to, where perf is not able to manually find the specific debug information, you can basically build ID cache -a and can import debug information manually for specific object files. And build ID list just gives you a list of what, sorry, you also need to have something going on, and after that, perf ID list can show you which build IDs get used by your current perf data. Oh, still visible? So, and there's another directory which is in your home directory, which is just .debug, so you manually can also link in debug information there, but you normally don't need that. Oh, sorry. So, slides are a bit out of order. So if you want to, for example, transfer perf data between different systems, so in case you for example, take a perf trace on some system and you want to analyze it on some other system, there's this command perf archive, which just creates a perf data tar reset2 file, and it also includes all the debug information which are relevant for you to inspect the specific perf data file. So that's basically the easiest way to move perf data between different machines. Later on, I will ask the question if someone or people can come up with ideas how to actually do large-scale perf recordings, or how one can maybe even do that network transparently. So you can always have something like agents which currently trace performance data. And I don't know if that's possible, but basically that's the way I currently use it. Okay. I don't know who of you actually has ever used perf. Okay, already quite a few people. So I guess some of the commands are not new for you. So basically, I guess what I started with was perf top, which is the command which has a top-like display, but it also allows someone to actually see functions which are causing most of the cycles currently burned on the CPU. And that was kind of cool. And I guess that was also the reason why I looked more into perf. So for those people who don't know, perf top, it basically just gives you a specific top-like view, and you can browse around and look at the symbols which currently acquire most of the cycles. So the default event which is currently used is cycles, which just basically gives you the number of, or just looks at where most of the CPU cycles are burned in which C function. Most of those commands actually share most of the command line options, so it's basically pretty easy to adapt things. So most of those commands use -e, for example, to specify an event, and so you can always transfer some of the command line options. The next command is perf stat, which is basically pretty easy. You can just specify a binary or a workload to run, and it just gives you an output of what basically it just gives you some numbers you can now expect. So perf stat is also pretty much extensible, so you can specify your own events for working with it, and you see a lot of numbers, but we can later see how we can actually look into specific numbers or what they actually mean. But it's interesting to just have a first look at maybe what performance problems have. And it's also a pretty accurate time-elapsing, time measuring way to check how long a binary is run. So, but most of the time in perf we use something like postmortem analysis. So we record, or we spend quite some time to try to find the correct ways to measure things. And afterwards we start a perf record, run the workload multiple times or one time, and then afterwards we just have a massive perf data file, and we try to analyze it. And so this perf data file is mostly generated by perf record, and it's just generated in the local directory. And perf record is basically the same like perf stat or like perf top, so it just samples events or counts events, and it just creates a file like perf data in your current directory. And further on, most of the commands which don't do analyzing or don't do directly insert stuff into the kernel work automatically with this perf data file. So you can, of course, manually say which perf file you actually want to use, but basically the default is the perf data. Sorry. And there are some other very important commands, which is, for example, the perf list command. Perf list is basically giving you a nice overview of what your current system supports for events you can trace. So we do have some hardware events, which are basically caused by the hardware itself. Those are specific performance monitoring counting registers, which you can program in a way that, for example, you can specify how much events, you can specify a sample period. So you just write how many events should pass until a specific interrupt is being fired. And when the interrupt is fired, the software can take a measurement at that moment and can copy that into the perf ring buffer, which then gets pushed into user space. So those basically are sampling events. You can either specify a frequency with which you want to measure them, or you can use sampling period or sampling count, which you want best. I even don't know what, we can later look in how that works. Then there are some kind of software events. Software events are basically events which the kernel fires itself without you having, or without the hardware doing anything. That's basically for minor faults or major faults or CPU clock cycles, which are pretty much easy to just, so basically there's just a function call or just some specific trace point in the kernel which just fire those specific events. We have quite a lot of hardware cache events which help you to look into how the caches are working if you have misses, or if you want to just improve your caching behavior of your current system. We will look a bit more into that soon. Branch loads and branch load misses and branch instructions are kind of new support in perf. I haven't played with them that much until now. It's also mostly because I don't use the new CPUs all the time, but it seems very interesting currently. So especially a very cool program which uses branching instrumentation in perf is AutoFDO, which is now released by Google, where they actually take perf captures and convert them to GCC profile-driven feedback data. So GCC can automatically, for example, do the complete likely and unlikely instrumentation, or the likely and unlikely annotations in the code without further thinking of the programmers. And the funny thing actually is that basically there was a talk on lately that even if you don't run the same workload like it was optimized or was captured with, it still gives you a huge advantage. So that's kind of interesting for branch instructions.
Hannes, yeah, question?
Yeah.
Could you repeat that part again? How the hell do you find out where the branches went? Is that what your question was?
Sorry?
I just wanted you to repeat the name, that was all.
So it's on GitHub. It's called AutoFDO. And support for the feedback, that's basically the project, Google/AutoFDO on GitHub. And the feedback driver for that is included in GCC 5. So it will be released around April, May with GCC, and then can be used by everyone. There are also some power management and other events. You have raw events, and then you have the specific trace point events, which are just, again, trace points which are specifically implemented in the kernel at some point. So there are some macros which allow you to very easily specify trace points and export them to user space, which kind of is also a problem. And you will later see that we don't have a lot of events for the networking part, especially TCP, because it is considered by David to be some kind of user space API, which must be kept stable. And so if we change something in the networking stack, we need to try to have still a stable trace point. And so there are not a lot of networking specific trace points nowadays. But maybe we don't need that. So if you don't know which event descriptors you're used for generating your record, there's this perf evlist command, which is quite handy. So if you have your current perf data somewhere, you can just perf evlist, and if you just specify verbose, you can see also the sampling frequency. So we currently sample with 4,000 hertz, and some other specific flags you can see which were automatically used by perf record. If you have questions or if you have comments or if I did something wrong, please just talk. Sorry,
So the question is what? I'll repeat it for you. What was the question? Repeat the AV listing. I don't know. I'll put it just raise your hand. I'll give you the mic.
So I said that basically perf is mostly post-mortem analysis, and there's a new tool coming up which is perf trace, which I more and more use as a replacement for strace, because strace is kind of very, very slow. It does a user space kernel transition on 2 times for every syscall. So and perf trace just uses the tracing infrastructure to emulate strace, which is much more performance, which is a big performance improvement, because perf trace just writes to the ring buffers perf provides, and user space can easily extract the data from there, and it's not per syscall overhead, but it's like bulking. And it does not yet have the full power of strace, but I guess soon they try to actually do that. And if I'm not mistaken, there are already patches out there which allow you to also use normal kernel trace points at the same time with the syscalls you use for tracing. So it's, for example, easy to see something like that you want to perf trace a send message syscall and look if something happens in between where you actually invoke the syscall and when it returned. Basically, it's also very easy to use. So if you just do a perf trace ls, you see it's basically giving you the same information like strace, and also does help you to actually interpret quite a lot of data. So nice thing is that, for example, you don't only see the file descriptor, but you also see the resolved path. It does so I learned that it does so by querying proc fs quite often. And as I said, in future, there's also the possibility to interleave the trace points into that. What's also possible, I haven't put that on my slide, is that basically you can at the same time trace, sorry, the mouse is not working that well. You can also trace page faults with perf, so if you want to try that, it should be possible. I have not yet used that feature, and I've seen it just 1 week ago. we can have a look if it generated something. No, I don't think so. But maybe it will work soon. So that's currently work in progress. Yeah, so after you have basically recorded all your data, there are multiple ways to actually analyze the data. Most of people, I guess, use perf report, which is a kind of nice graphical, so basically graphical user interface to just look at the data that was sampled. Depending on which options you used during the record, you can also inspect the call graphs, other stuff, and go into annotation mode, so you can basically see where you could improve performance. We will later see more examples about that. There's basically perf script. Perf script without arguments just gives you a very easy to grab and maybe even shell process way to look at the data. But it also allows you to implement small scripts with Perl and Python, which already, we will see the data on, which already have the correct callbacks to the correct callbacks for all your events, and they already pass the specific arguments they collect in the kernel by Perl or Python arguments. And there's perf annotate. Perf annotate basically gives you an assembler view or a source code view with source code and assembly interleaved, and annotates you which hotspots perf found in your code. We will see those tools later on a bit more closely. So if we now try to play around with perf, there's this setting. So basically perf, depending on which distribution you use, you're not allowed to use perf as normal user, but I tend to actually on my systems to give full access to perf by my users, because I normally don't want to always write sudo. So most of the time I think it's perfectly okay if you are on a single user system that you just enable perf for normal users, and it makes some stuff more easy. Okay. Any questions or comments? So there are basically four areas if we look at networking performance in the current kernel. We tend to have algorithmic complexity, which is basically if we look at how algorithms are built. So if we, for example, have what recent optimizations in the FIP table by Alex, which did give a lot of gain in terms of performance. There are also other things like how much code we actually traverse and where we can put shortcuts. So, and where we have to do a lot of looping. So those are basically things we can improve by mostly looking at the code and trying to come up with new algorithms, or I don't know, improve caching at some points or install fast parse. Then a huge area which nowadays comes up more often is memory access behavior. So we have multiple CPUs fighting for the same memory locations all over and trying to exploit parallelism, but actually not really exploiting it in a way that they contend often on specific memory locations. And so that's basically a problem on scalability in the current kernel. So cross CPU memory access mostly stalls multiple CPUs and causes fault sharing, or fault sharing also slows down multiple CPUs at the same time. Then we have, it's also a bit like algorithmic complexity, we have assumptions on network traffic. So for example, if you look at specific offloads we have in the kernel, like receive offloads, they are only working if, for example, specific trains of packets are received in a short period of time, so they can get aggregated. And if a packet, for example, is missing from the train, then it gets received too late. the packets might already be flushed to the upper kernel for processing, so it could not aggregate the kernels, and so we do multiple fib lookups, we basically do everything multiple times for all those packets. And we will also see how perf might be able to help us with reasoning about those assumptions. And I don't know how the time is working out, so maybe we also can have a look at raw instruction throughput. This is not mostly about perf, but there's also a tool called the Intel Architecture Analyzer out, where you can just throw some pieces of assembly code into it, and it will simulate the pipeline of a CPU. So, and you can check if maybe reordering specific lines or instructions can give you a higher throughput or better latency. So, in the first field, algorithmic complexity, it's basically most easy to just really use something like perf top and just try to sample cycles, in my opinion, to find the most used or heavy-weighted users in the system. And for that, basically, a new syscore was implemented. So this is basically just looking a bit how perf event or how perf works and how those PMCs are programmed. There's one syscore which is perf event open. It has quite a lot of arguments, not that many, but it's a bit more complicated, and I guess one of the longer main pages in the kernel manuals. You can open it for specific kind of event, like for example for the hardware cycles, like we saw in the perf list command, and it can do, and it will return you a file descriptor, which you can do two kinds of things, like sampling or counting. So if you specify a sampling event, you normally just memory map a ring buffer from the file descriptor and just process the ring buffer. In case you do something like where you don't want to sample stuff, like just counting, you can just use read and normally get long values from the file descriptor. Yeah, as I already explained, we have quite a lot of event types, which are which you can specify as events in perf event open. We will look at a few of them later on. So specifically for hardware events, you can look at perf list HW, which gives you the current list of hardware events. -C and -F, they allow you to override the frequency and or the sample period. And as I already said, that perf EV list -V shows you the perf event or the attributes to the perf event more closely. Yeah, so I actually, at that point, I would like to have most of the people who want to participate in that maybe to try out some of the commands I showed so far, and maybe just trying to perf top -E some specific commands from perf list, if you want to. Otherwise, I can just also go on and we can do that later on if you want. So either you just now try to play around with it a little bit for, I don't know, 5 minutes and just look at the counters your system provides and look at perf top or perf top -E, what you actually currently see on your system as most showing up functions. Or I can just go on and finish the slides and later on in a closer group do that. Okay. Okay. Okay, so who tries to now get perf working? currently? Okay. Where are you? What's your problem, or are you just currently installing it? You already got it working. Okay. Okay, so I guess the most hard, the the worst part is mostly always to find a given workload or a benchmark which tries to actually show the performance problems. And unluckily, I cannot help you with that. So most of the people, I guess, just use Netperf for that. And so, for example, now if we look at what perf top can do, so the basic option is just perf top, and it will show quite a lot of lines where you can browse into. There's also always a help with small h, with the letter small h, where you can do quite a lot of other things, but we don't need to do that right now. The interesting thing is basically how to deal with events. So perf top mostly allows you only to trace one event at one time. And we now want to focus a little bit on the hardware events. So hardware events also have some modifiers. And so basically it's the same thing if you do just perf top or perf top dash e cycles. That will give you the same view. So the dash e cycles is a default. But over time it was noted by AMD and Intel, I guess at AMD first, that because of the high the length of the pipelines and when instructions get retired and actually are dispatched, there's quite a huge latency between them, especially if you think about memory reads and memory writes. And also if you, for example, like you have atomic operations, and atomic operations just does not stall, but the atomic operation, which is part of another code stream later on, stalls because of your memory barrier you did before that. Sorry, memory barrier is a fence, not memory barrier in the sense of a compiler barrier. So they started to add specific a new subsystem to the CPUs, which at AMD is called EBS, instruction-based sampling, and PEPS at Intel. And what it allows you is that basically you can, in some sense, direct the CPU to try to get more accurate samples from the CPU. So you can basically, I will just quote what the, what the man page says. It's the man page of perf list. So you can specify the p modifier multiple times. And if you don't specify p at all, you basically say that the CPU can give you just any kind of location where the event fired. If you specify p one time, it gives you constant skid. So basically, you always have some kind of constant offset from the actual location. And you can try to level 2, basically on AMD and Intel system, where it tries to actually reduce the skid as much as possible and give you the instruction where actually the fault is. So depending on your CPU, you can just try to put there as many Ps as possible. So at some point it will just say that your precise level is not supported by your current CPU, and you have to remove Ps until it's possible. So that's basically how you do it. There's a modifier also for K, which says that you only want to enable kernel-only accounting, but it does not make a lot of sense for cycles, because basically, yeah, you can just try to clean up your perf top display a little bit with it. So, were there any problems, or did people experience any problems who tried to do the perf top examples and got error messages? Not okay. Pardon? Was there a question?
How it's a cycle and then a column PPP or what?
Double colon, cycles, double colon.
Double
PP.
column and then PPP and
Yes, and the number of P's specifies. So double colon and then the number of P's specifies the precise level the CPU should use for that specific hardware trace, hardware PMC. You can also try. So there are quite a lot of other different flags which you can use. So I mostly am interested in kernel performance. So I most of the time use the K for kernel counting. But you can also try user space accounting if you are only interested in user space and user space events, and also specify specific flags that you only want to have performance data out of virtual guests or in the hypervisor. So perflist basically lists the ways you can use or what specific things you can trace. There's not everything in the man page, but most of the stuff is. So what you can do with it is, if you look at algorithmic complexity, if you hit a specific worst case workload, it should basically be pretty much at the top of perf top, and you can try to find ways to solve that. And as I said, you can also sometimes try to introduce caching and get around the algorithmic complexity in some places. Okay, let's look about reasoning about at memory access behavior. So I took the examples from Eric Dumaset's patch, which actually I didn't know that actually it gives such a big difference in performance, where he mostly just removed the read modify writes in the MLX4 code path by using volatile reads and volatile writes to the ring structures, and it reduced fault sharing quite a lot. So actually, the code got more performant, and yeah, it's a little bit, I guess, of magic how to see stuff like that. But perf also can try to pinpoint such locations, and there also are new features in current CPUs which help with that. So in that specific case, compilers, especially GCC, which we currently use in the kernel, they do not really help to for example, reason, or they don't reason about memory loads and memory stores that much like maybe we would want to. And also they currently have no model where they can reason about if they should, for example, issue prefetches to the memory automatically without the programmer knowing it. I guess in kernel we don't want that, because also I heard that, for example, prefetch also always causes memory loads on some CPUs, so you cannot just use the compiler for that. So sometimes we need to do manual guidance. So pacing memory access across functions. So the cache lines are loaded from memory or written to memory without stalls, or avoiding modify write instructions, where, for example, you can just use some local stack variable which has the same value as the in-memory variable which is shared, and use that for updating stuff. So, okay, this is like basic knowledge. In case you do performance analysis on the kernel, there's this rule that you basically should push hot elements of C structures to the front. So that basically the reason is that all CPUs only fetched complete CPU cache lines from the beginning to the end. And so basically, if you wanted to have the last value of a cache line, the CPU had to reload or had to load all memory from the memory, and then could just start the instruction again as in the moment the complete cache line was in the CPU. So nowadays, more recent CPUs have something like early restart, where in the moment where the memory really comes in, the instruction is restarted at that moment and not after the complete cache line is actually loaded into the CPU, or even the new Intel Xeons. I don't know when they actually did implement it. They implement something like critical word first. That's an extension where basically the concrete memory location gets loaded into the CPU first, and afterwards the complete cache line. So maybe in future we don't, especially on x86, maybe we don't need this rule anymore because the CPU will do it correctly for us. Yeah, so perf has quite a lot of memory, of cache hit traces or events we can monitor. I don't actually have a scheme or what one can do actually to try to optimize such stuff. It's basically also about finding workloads and then playing around with the specific events. I guess I don't know, there will be some exercises later on. A new tool came in, so this is also related to the PEPs, to the precise levels I explained earlier, which got introduced with PEPs and IBS. It's perf mem record and perf mem record and report. And the interesting thing about it is that basically PEPs and IBS do not only give you more precise level, but they also provide you with the specific memory address which caused the hit or the miss in the caches. So what perfmem allows you is actually to see which memory location did hit or not hit the cache. And it's basically a wrapper around perf record. So most of these perf log or perf mem or perf kvm commands are basically wrappers around record which just do some fancy stuff with the arguments. And in this case, they use the CPU mem loads with 2 precision levels. And there's an opposite command which is perfmem-tstore, which shows you the stores to the memory, and it's basically an alias for the CPU mem stores with double precision level. I can show you something like that. So I just use a small tool like stress, which now just has 10 instances with just malloc and free stuff, and we just can run it for a small amount of time. Oh, it's a bit. So after I just pressed Control C, so we now have a perf data file, and I can, by just running perfmem report, the report tool just opens the perf data file and displays the results. And that is basically what we get. So the interesting thing is that instead of using some other tool, we also have the data symbol with us. So we can now actually see at which memory location the hit or the miss was caused. So you can also, like with H, you can sort in it and you can look it up. The problem is basically that in a lot of moments you don't have any valid memory locations because of dynamic allocation of memory. So sometimes you can guess, like for example, if a pointer is in a specific slab location, you can guess by looking at your slab store in which region the pointers are, and maybe you can associate them back. But I didn't have that good results with that actually. So yeah, so this is basically a feature which also came in with the PEPs and IBS support, and since that was implemented, every event has a specific additional data associated with it, which basically says at that moment which memory address is causing the specific event. So yeah, so if you wonder about the CPU/mem load/pp, event style. This is not documented in perf list. It basically is a path, or you can interpret it as a path in sysfs. So most of the events are also duplicated in sysfs and sys devices CPU events, where you can find most of the events also, and you can specify them like you have seen here, just specifying CPU / whatever / flags. And in some cases, like for example, if you want to see PCI Express performance on AMD systems, there's, for example, a specific non-CPU node for AMD North bridges, where you can then specify specific event masks for the North bridge if you want to see how PCI Express data, for example, is moved around the bus. There are also some other cool tools, but this one is unluckily not available by default because you need to enable a lot of debug options like logdep for that. But if you do that, it basically allows you to actually also look at contention problems in logs. So without perf log, if you look at contention problems, you basically only see the raw spin log functions showing up, and you don't have any addresses where they are associated with. And as soon as you have the perf log command, I'm currently running a logdep enabled kernel, so I can show you now. So if we know, for example, I don't know, I hope this generates some kind of pattern we can use.
And we can
Yep.
hardly see what you wrote there. Can you read it, like the command line you did?
The command line before,
Yes.
it was basically this here. Just arbitrary generating some SKBs in the stack. And now it generated a new perf data file, and I can now perf log report it. So what we now have is basically it's still a bit too large. I guess if I pipe it into a less -s, it might. Oops, sorry. So, but it helps you at least to somehow identify the specific logs, and so it gives you more of a better view of what contention is actually causing in your system. You can also use perf script afterwards and debug the logs yourself, so you normally are able to actually identify the logs. And otherwise, you can also just check it with proc logdep, where you can reread the specific kind of logs and also get the specific log class from. Okay, so now those are basically all the trivial commands, and most of the time, if you do perf list, you can either look it up or check what else. Sorry? Yeah.
Yeah. So about logdep. Logdep is quite expensive, so it's very disruptive. I usually use -G to get the core graph. It basically works for every kind of event.
Yep.
And usually by looking at the core graph, you can have a pretty good idea where the log contention, if any, happens.
Yeah, that's also true. I just wanted to present the tool because it's also a special tool in the perf repository. Yeah, so Eric is correct. So basically, the call chain, which you can get with perf record -g, and also later on see in perf report when we do some more exercises, allows you to pinpoint which specific log, not based on the data or on the specific log location, but on the code path, is causing the contention. So Andy Clean, who is working for Intel, has a pretty amazing suite of wrappers for perf, which is called PMU utils. You can find it at GitHub. I hope if you have internet, you can now git clone it, because it also, I hope you have Intel CPUs. You can clone it, then we can have a look at the tools a little bit more, and you can maybe just play around with it or have a look at it. So basically it's on GitHub, PMU tools, where you can clone it, and I can show you some more things you can do with it. I will also only show a small part of what is possible with PMU tools. He also has tools to actually do performance gathering on a algorithmic way. So if you, for example, have specific workloads and you want to analyze them more concrete, there are some wrappers around that. And we will also only look at the CPU low-level features which those tools provide. They don't add any kernel code, but only basically wrappers and helpers for specifying CPU events, which otherwise you would normally specify as raw performance or raw counters, or even in a more abstract way. So I guess in case, I don't know anymore, if in case you have cloned the tree, there's a tool which is called OCPerf. And OCPerf basically just invokes some other tools if you start it for the first time, and it downloads a mapping for specific CPU events to raw descriptions of raw counters, which then can be fed into perf. And I guess it's somewhere in the home directory, I don't remember. Or so you basically can also just event download the file, and it will just download your specific JSON files which represent the counters to your CPU. And yeah, like it saves it like root.cache PMU and events, and then you can look at it. So if you use OCPerf list to look at all the possible
Can
events.
you show the link again? Maybe we can download it now.
Ah, sorry. Is it okay now? I guess you just have to use it with a web browser, and then there's a link to the Git repository. Okay, thanks. Also, git clone to that address just also works. So if you use the OCPerf list event, it just gives you basically the output of your previous, what we had in perf list, so nothing new here. But at the end, suddenly there are some new events are showing up. So you now have basically access to most of the internal PMC instructions you normally don't see in perf list. And also they are a bit more documented, so you actually can think about what those specifically do. So if you want to look those up for AMD, there's it's actually quite easy. So you can also just use. I don't have an AMD system with me right now, and what you do basically is that you just use the AMD/_NB namespace, and you specify the event and the mask from the manual, and so you can do the same things you can do with the off-core events with proper and pretty names on AMD systems. So So what you can, for example, see that, for example, if you look at a lot of memory-specific issues, you have the possibility to you can, for example, specifically trace where your cache lines in layer 2 are switching from the specific MUSI states. I hope MUSI is known to the audience. So basically in the cache, there are always states associated with each cache line on if the cache is shared between different CPUs and can be read. Currently, if it's invalid, it must be refetched from different memories. And if it's, basically all those states. If you don't know about it, just, I guess it's pretty easy to just still have it open to look it up in Wikipedia. So there's MUSI and MUSI states, different, depends on the CPU you are using. And it just allows you to have a look at when specific code evicts specific data from the cache lines. So if you want to, you can now just play around with it. And maybe just if you have some user space programs, use OC perf -e. You can always include as many events as you, not as many, but you can mostly add multiple events at the same time. And so you can check where and when specific memory is being evicted from the cache or is requested for ownership. So basically all other memory is invalidated and your specific CPU wants to have full access to the cache line. Sorry? Sorry, I didn't understand you. The command line for, so I can show you just like how to do that. So you use the OC perf command, and you can just specify -e record, and then you can just pipe in multiple events like that from this specific from the output. Sorry. And then you can run your workload on it, like sorry. And it will now measure the cache lines, where the cache lines get faulted in and faulted out. And if you run the command, you can use any command or even a sleep with -a for monitoring your kernel. And if you then report the information, you basically have an overview of where your cache lines got into exclusive state or were invalidated for the duration of the command. So I would like, I think if you want to it's very interesting basically to look around what commands every CPU has, and also to always check the CPU reference manuals, which a lot of those events are actually described in more detail. Always also be aware of that not all commands are supported by all CPUs. So sometimes you try to trace something and you think that you don't hit the specific event, but maybe it's just not supported, and you always get back a 0 counter. Most of those raw counters can also be, like I said, so basically you can always use the raw counters with everything else. That should also be no problem. So you don't need to have this utility, but can also specify everything by perf. Okay, we are now leaving this hardware-specific region a little bit and go into the assumptions on networking traffic, which deals a bit more with tracing and actually reasoning about logic in code. Like, for example, we now have different assumptions where we can actually speed up network traffic in the kernel. One is xmit-more. So xmit-more allows to not do the MMIO barrier or MMIO write on all SKBs we transmit out of a specific interface, but we can now batch them and, for example, can send 5 packets at once with only one time touching the expensive tail of the tail pointer. During receive offload, we often see, or we hopefully get packet trains, which generate, which result in aggregated SK buffs. And we sometimes also want to know, for example, if the aggregation is working and if it really does aggregate stuff. We can, for example, also monitor if root caches evict destination entries all the time and try to reacquire them, or checking if flow-sensitive if the packet steering does not work correctly and we have cross-CPU calls from some code. And to do that, basically, we can specify probe events on our own. So what we now try to do is that I have an example with xmit-more. So we try now to pinpoint if we currently really use xmit-more on delivery during the delivery of packets, and we can do that without any trace points. Or without any predefined trace points. So we only do specify probes on our own and try to reason with the source code to now find a way to specify a node or a probe which gives us this information. So hopefully, I guess if you don't have correctly working debug symbols, that's currently the moment where it will blow up. So in the networking system, we have a few functions. So basically, the most important command you know will see is the perf probe command, with which we actually modify and install probes and remove probes. And like the chaosim information, we have a perf probe dash big F, where we can see all the functions where we can now insert, or which we can reference with perf, and where we can try to look into and check if we somehow can install probes in it. So if you look around, basically we have quite a lot of functions. We also have most of the networking functions in there, so quite a lot, I guess. Sorry. So you basically can set a lot of trace points already in the code in the kernel without actually using anything predefined. So in case of xmit-more, there's a problem that nowadays we tend to use a lot of static inline functions, and those static inline functions are not representable as functions if you look at the binary. So because they get expanded inline in the source code, so there's often the problem basically that you need to dig down, or you need to find actually a function which is not static or which is exported, not exported in the sense as export symbol, but only exported from the object file. So it does not get optimized away. Yeah, sure.
I saw a couple of other profilers managing to cope with the static inline and shows the breakdown of the static inlines function.
As you will see later on, that perf can do that too.
Ah, okay.
So in case of this xmit-more flag, I decided to go with dev xmit function. So I can now try to perf probe -f -filter and just use this wildcard, and we have quite a few functions which match that. So basically, if you want to search for a function, it's basically the fastest way to look around. I use it quite a lot if I want to just try to add filters, and you can even use Xarch and then install quite a lot of probes at the same time for that. You can use wildcards at a lot of situations. So even if you want to, for example, perf record something, you can always specify star, and basically you match all the probes you already have installed. So with wildcards, you can quite easily get a very good overview of what is happening in your system. But we now try to get a bit more deeper. So we now have found this dev-xmit function we want to use, and so now we need to find out if we actually do get so if the xmit more flag gets actually set by the code. So what we do is we look into the source code of dev-hard start xmit. We can do that by -big L. And what you now see is that basically a listing of the source code, and the lines which are numbered are lines where you can install trace points. So it's now possible that, for example, you say, I want to install a trace point on a specific line, and then on that specific line, if code actually reaches a specific line, that trace point actually gets fired. So what I did here was I decided for line number 17. I don't know if it's correct anymore, but I will just go on with it. And there's another option which is called -v, where you can, at a specific location, ask perf to give you all the possible variables and symbols you want to trace. So what we now do is asking perf what variables are in your scope we can actually get into the perf probe, so we can actually relay all those variables to user space, and later on check on the specific value. And as you see, if you look into the xmit1 function, we specify the Boolean. So xmit1, the last argument basically is a Boolean, and if the Boolean is set, then we basically tell the driver that we will have a train of packets now going out of the driver. So what we want to do is basically check if the next pointer is null or is not null. So we need to specify a new probe. And do you see my mouse? Okay. Basically, it's already here, so I'll show you a few more tricks what you can do at the same time. I guess I cannot copy paste it in the. So I just have to type it by hand. So I define a new probe which is called DHSX, just shorthand for dev hard start xmit. If I wouldn't have specified anything, it would just use the function name as the probe name. Pardon? Oh, sorry. If you look at the perf probe output sometime, you see that stuff gets optimized away, and you sometimes have to pinpoint a little bit more because, sorry?
Just enlarge the font. Or enlarge the font. That we can
Sorry.
see.
Okay. Okay. So you always have to check where next is actually set, and sometimes because we are now working on line information, and line information is not always correct. Like for example, there's no real comparison if next is 0 or not equal, but it will just pass a pointer down in xmit1, which is a static inline function.
I think what's not clear is that previously you said you want to see line 10, and then you run perf probe big
okay.
V, and you specified 17. That's what's confusing.
So the reason is basically that I don't know, at the time I did this, I was not able to inspect the next pointer at line 10, because basically xmit1 is static inline function and it expands the equality is done later on in the static inline function. So I just played around with it and tried the different locations or the different line numbers, and line 17 in the end looked like a good hit, and I also verified that with the disassembly code. So if I don't know if it works right now, so we can try to. We can just perf probe on line 10, and here you have the effect. So xmit1 is a static inline function, and it now shows you at which locations in the source code this function actually gets expanded. And the problem is basically that we have at one point, this is this point, we actually have access to the next pointer. But if we would now insert a perf probe on line 10, we would have the problem that the expansion at that region, so at dev hard start xmit plus byte offset 72, would not give us access to the next pointer. So in that case, I cannot literally install the probe in line 10 because it would fail, because one of the locations where the function gets expanded is not able to fetch the next pointer. So I could either go the route and install only the probe, or install two probes at byte offset 79 and at byte offset 83, or I can just go with a probe below that. Okay. So I use line 17. I now define an argument I want to extract from the kernel, which is the interface name. It's just my name, so you can write everything there, and only what is after the equal sign is responsible for fetching the name. So we see that at line 17. This is the variables I have available. So what I can do now is I say that I have this net device and I want to see actually on which net device the current logic happens. So I want to pretty print the name of the net device. So I can just use dev name and specify the type as string. So it will just give me a nice string for the specific line when the source code hits it. And at the same time, I want to extract the xmit_more pointer, which I know where I currently just extract the next pointer, but in reality, basically, I want to have a Boolean indication if the specific pointer is 0 or not 0. So we can then insert the probe, and perf now tells us that basically we can, just by running this command, we can now start with tracing. I don't know if it worked, but we can. So we have no samples, but we can now do some other commands like let it sleep for a little bit longer, and hopefully, in case we connect to the Google servers, we can at least get some visible effect of that. So let's see. Oh, sorry, I was thinking about GRO at the moment. What would be a good example for that? So basically, it now tells me that xmit_more is null, so we don't have a next pointer, and so xmit_more is currently not in effect. Sorry, I can come up with I don't want to run out of time and don't want to set up netperf or something like that right now to show you the effect. So in case we currently, it uses xmit_more, I would have the address of an SKB being specified right there in the xmit_more, and so I would see that basically I do now at the moment batch packages. It would be, yeah. So this gives a lot of options actually what you can do even without tracing, or even without statistics, or with different kinds of hard-coded trace points in the kernel, and you can have quite a lot of insight to see a lot of insight gains in what the kernel currently does. I actually now wanted to hope that people might be able to find a trace point or do that on their own, so they can look into how many packets in GRO get aggregated just by writing a probe. Do people want that, or should we do that afterwards if you come to me? Okay, no response. Pardon? So, okay, first question, does everyone know what GRO actually is? Sorry. So,
Maybe you can show that if you want.
yeah, I will. Basically, GRO is a way to aggregate packets in. So what GRO basically does is during one NAPI call, so it tries to fetch multiple packets from the hardware at the same time without any rescheduling. And if the packets match up, so for example, if you have 2 or 3 TCP packets and they match up in sequence numbers and in flags, and you just aggregate them to one TCP packet and send it up the kernel. So instead of actually processing 3 independent TCP packets, which would be much more intensive if you think about all the algorithmic complexity and stuff like that, it would just process one packet, would do one routing lookup, would do one append to the socket queues and stuff like that, would only fetch or only log one pointer. Yeah, and basically the problem is that GRO is, we kind of rely on GRO today for good performance in the kernel. So it's always best to actually have this aggregation in place. And yeah, so exactly what we now want to do is trace when, or what we want to check when aggregation is actually happening, or at which point we can use that. Okay, those who know actually what GRO is maybe can try themselves to now resolve this problem, and otherwise I will now help a little bit. So basically all the code you need is in netcore-dev.c. That's basically where you need to look at. So it's not that easy, and I currently don't remember the specific trace point myself, but it should not be too hard either.
Just, could you repeat your question? What was your goal here? Because GRO count here is not exactly what you.
So I would like to find a way to where we can actually trace how many packets, so how many TCP packets got aggregated into one SKB.
So that would be the GSO SAGs you find in the SKB shared info. Because GRO count here counts the number of different flows active in the GRO engine. So that's not exactly what you want.
I currently also have to look around and don't know specifically where to place the probe. But I guess this location looks like something we could actually use. Do you agree, Eric?
Eric, I think he wants to find a place where you flash it and.
Pardon?
Yeah, that would be that.
Okay. I just wait a few seconds, maybe until people can catch up. If you want to try it yourself. So the function is called NAPI GRO complete, in net/core/dev.c. So what you normally do if you want to try to find a way to or get an overview, you just look at the lines in this function, and with -l like I showed before, so you see there's at least some way where you have access to the SKB, and you could somehow think about extracting this count. So, for example, line 9 accesses the NAPI-GRO CB of the SKB and compares it with something, so it must be somewhere around in the memory. And we need now to get hold of that specific count and trace it or give it back up to user space. So we can just look at what we have available at line 9 by using -v. And we actually see that the SKB is visible for us right there. So there's another problem now because, sorry, we do this NAPI-GRO CB stuff. So NAPI-GRO CB has a problem that basically it's an kind of unsafe cast, and we now need to specify memory offsets in perf. And luckily, kprobes allows us to do that. So we can specify a fetch arc, so something where we fetch memory, or where we have a symbol available with an address which can be resolved by perf, and we can specify an offset to that. So it allows us to peek into the CB section of the SKB and extract the value. So for that, we need to add a new probe and NAPI-GRO complete. And actually, I again want to know on which interface this is happening, so I use skb dev name.double:string, so I get a name where the SKB was arrived. And now we need to look into how we can get access to the specific offset. So we know basically that we can just use the SKB as a base pointer, and we now just need to look into the offset. And unluckily, I guess I want to check if we can now recalculate the offset, and for that I will just reuse von larger. I currently switched to the debug kernel of Fedora, so I need to redo the calculation where the specific SK offset is. So we have this tool ph hole, and now I just need to extract my current VM Linux to do that. So what this tool allows us to do is that we can, in some comfortable way, see how C structures are laid out by the compiler. So I can call it on my VM Linux tool and specify -big C that I want to see the skbuf structure. And now we see our big memory hog which gets allocated for every package. And it's actually a pretty handy tool, and I guess you should actually include it into your repository of debug tools, because it can show you where cache lines are, where you have still bits and bytes, where holes are in your structure, And also, it can even automatically, I guess, dash big R. It allows you to even automatically reorganize your structures to remove the paddings. But the problem basically is that NAPI, so we can only find the CB in here, which is basically this part of memory, which starts at memory location 40 and uses 48 bytes. So we now need to also look into we now need to also find the offset in the NAPI GROCB. I kind of think it's maybe easier to actually try to do that via GDB and just extract the location out of the disassembly. So let's see. So we have this compare with 1 and RDE. I guess it might make sense if that's the memory address of our SKB, and then it seems natural that OX3C is basically the offset to the SKB into the CB. So what we now can do is that we basically just specify the OX3C here, and that's our new trace point. Oh, sorry. Yeah, sure, sorry. Does anyone remember the type? It's U16, I guess. Pardon? I cannot do that because of NAPI or CB. I guess it's U16, I guess. I have it later on in my slides, I guess, somewhere. Yeah, it's U16. Right, it's even at the same address. So I can just specify unsigned 16 here, and it will basically treat this value as an unsigned 16. You can do that for signed and unsigned 8 until 64. And there's also some special constructs how you can specify bit masks. No. Okay, I still have a problem. U64 doesn't have a okay, let me just check what I don't know why I specify U16 and it says that U64. Pardon? That's true, yes. No, it's also, I'm not sure why this is happening right now. Oh, there seems to be a parse error somewhere. I can just remove that one. No, that's not. If it's that one, okay, that's. Still not working. So perf-d probe wildcard does remove all probes from your current kernel. I have no idea why this is happening right now. Yeah. RDI was wrong. I would have to use DI because I'm not allowed to use the R specifier, the length. So it did work with %DI. So now we can try to do that, to use a probe. And I now just try to contact Google servers and send a whatever. And it hopefully tells me that I have some kind, no, it did not aggregate. Hopefully that does work at some point. Sorry? No, I want to be that. What else can I do? Yeah, I can do so. That's loopback, it does, yeah. So I need to find a big image. I can, yeah, I can do that. Oh, I guess I don't have any internet anymore, so that's a problem. Or do I? I just keep it running. It does still work, so I try to. Yeah, I got aggregation. Okay, so as I showed you, if you use a dash v, you actually do see where inline functions also get expanded. But there are sometimes you really hit problems where it's really hard to find the assembly, especially currently perf annotate does not allow you to if you have huge amounts of static inline code into static inline code, it really makes it hard to follow that even in GDB, and sometimes GDB just stops to expand static inline functions at some point. I guess the level is 8. And after that, you're a bit screwed. And the chance that you can actually inline, that you can actually specify probes on such code is not that good. So it sometimes actually makes sense to modify your kernel code we have this no inline defined in the kernel, which expands into this attribute for no inlining, which then basically allows you to specify a probe point directly on this function. You actually, it's very often that you actually have to move code around, so from the header file into an object file and then update, add a prototype for that, and maybe even export symbol that function. But if you really want to trace it and make it your life a bit easier, you can do it like that. If sometimes stuff really gets very, very strange, you can also add your own volatile variables and just extract some data into this variable and then use it with perf to.
Excuse me?
Yeah, sorry.
Next question. But even if I remove the static inline from some of my function, sometimes the compiler can inline it anyway.
So that's the reason why you can specify no inline, and no inline really will force the compiler to not inline the code. But it has a semantically different behavior. So if you look, for example, at the GCC manual, there are different kind of how static inlining works, and when static inline does not become static inline. So for example, if you have a static inline function, but you also have a function pointer taken from the static inline function, it will generate a locally static inline function which is not inline anymore in the specific object file, even though it was only included by the header. So you see the problem? So you suddenly start to have multiple same named only local static inline functions in multiple object files, which then get linked together.
Yeah, I understand. But sometimes it's hard with the kernel. We tried not long time ago to compile the kernel without optimization, and apparently
without
it cannot
optimization,
be made.
I don't think that works actually.
Yeah, it doesn't work. Yeah.
Yeah, because the build back on macros actually they depend on the removal of the function calls, and if you leave them in there, you actually have undefined, not resolvable linker errors.
Yeah, yeah. But I just wanted to say, I said it before, maybe we can look at it sometimes, that I did see some other profilers like OProfile and VTune.
I actually have to say that basically I don't use it anymore. So I actually kind of always find the correct pro point, and even though I do have inlining effects a lot, and current disassemblers are pretty bad, I think. So maybe you guys can tell me if you saw some other disassembly tool which you use. I basically use GDB with Emacs. Or sometimes on systems where I don't have the setup, I just object dump the whole VM Linux binary into one large file and wrap around. That takes quite a while. Basically, the problem is that sometimes you need the disassembly to source code equivalency, and that's sometimes really hard to get if you have a lot of static inline functions. So, and that's not a problem of the tool of perf per se, but it's a problem of you trying to understand the code. Yeah, so basically what you also can do is using volatile variables to extract stuff and then just poke on the stack. There's a lot more in what you can actually use or capture. There's also the perf I can show you. Perf probe -f -externs, which also shows you all the public visible symbols at that point, or I can do that with -y def hard start xmit. Oh, sorry. So it also gives you the information about all the globally visible symbols at that moment, which you can also use in your pro points. Yeah, basically you can try or actually try to get everything out of the stack. Sometimes you need a bit more brain power to do that. Like, for example, if you want to extract IPv6 addresses, you have to use multiple U64 arguments to do that, and then reassemble that in code.
I have some question.
Yeah.
What happens if you dereference a null pointer? Have you tried that? Like skb dev name. What if
we can try to do so? I don't know. Let's see.
Yeah, it's in this case the skbdef will be multiple prop kernel read, so it doesn't care. So it will just
I guess so. Yeah,
returning zero.
I remember. I'm not sure it anymore, but it uses some safe read memory function which checks for a lot of
it goes
eventualities.
To the prop kernel read that it will just like it disables defaulting. Just
so
it
what
will
we
be
can
fine.
we can try it. Like I have this xmit more thing still around here, and we can now just it's an SKB, so we just dereference the def, and I give it another name. So it will perf record. Should already work. Yeah, so it just gives me a null pointer Eric, even if I have a dereference. Okay, any questions so far? So what else is interesting is that, for example, you also can do that with return values. So often return values are not that easy to trace. So there's some special syntax to do that. In case of this dev hard start xmit, you can specify a % return on the function name, and the return value is in the $redval variable. Question?
Yeah, so the one thing I don't fully understand yet is there was a method to modify an offset. When would you actually use that, since it didn't work for the SKB to GSO pointer? Why? When can you actually use it? When is there cases where you don't have to use the actual register value or the actual register name?
Actually, I'm not sure why. I will have a look at it. So it showed to me that basically at that point I have the SKB available. Actually, currently there are quite some bugs in the code which are already fixed upstream. But for example, this return and red world thing I can also not show right now because there's a bug in it and it already does not correctly register the probe point. But in older or better, so in other kernels it currently works, but my kernel is currently not able to do that. So it might be a bug, I don't know. So there's also differences in perf does have 2 ELF backends. So you sometimes also get different results if you use ELF utils or the libeLF stuff. So you always have to double verify if everything really is as expected. So if your debug info sometimes is messed up, so for modules you sometimes have to actually -m and specify the debug information for the module. If you, for example, now start to trace in IEEE, in the wireless stack, this is just an example. You just have to specify where the extracted debug information are for the specific module. Normally, it should work without doing that. And the cool thing is that basically works everywhere, not in the kernel. So you can use this -x, and you can look into user space too. So all commands I just showed you are also available for user space. You just have to specify either the shared object, and also you need to have the debug information available for them. And then you can do the same thing in user space, basically everywhere, which is kind of cool. Okay, so basically if there are, as I showed before, but I don't think I do any more examples on that. You can also specify raw events, so you can easily, I don't have any good examples for that right now because OCPerf mostly covers all cases for Intel CPUs, and AMD CPUs are also specified pretty easily, just looking up the tables in the manuals and using this AMD_NB for Northbridge, and specifying the event and the mask value and the flags, like PP kernel only. You can do some other pretty cool stuff. Like for example, if you are in GDB, you can extract the address of the memory location of a specific data, and put a breakpoint on it and trace the breakpoint. So that's, for example, in this case, we extract the FIP6 serial number, and every time the serial number is getting updated, we know that basically we have a full caching validation going on in the current IPv6 stack, and we can, for example, trace that with that command. That's also pretty handy. Okay, I can't, maybe if people come to me, I can show you how you can work with perf script. So basically perf script also has some pretty nice scripts people normally don't know. There's, for example, this some predefined scripts which are sent out with the perf distribution. Interesting for kernel or for networking people is mostly the net drop monitor, because perf is, I learned that perf is probably more often installed on systems than Dropwatch. So you can also use the net drop monitor, like perf script net drop monitor, to extract the same information. There are quite a lot of other cool scripts I would like you to play around with, like Netdev times, which basically places a probe on the netrx action and the return of the netrx action, and it kind of gives you, it's not very granular, but it shows basically where most of your time is spent during the execution of the soft IRQ. Yeah, just play with them and also look into the comments of the scripts at the top. Basically, they give you much more details what they do. Okay, I will skip this section now because I only have 3 minutes left. Do you have any questions? Okay. Otherwise, thank you very much for your attention, and that's it.